Back to normal. Today's experimental mathematics seminar speaker of Rutgers University is Professor Michael Kiessling from Rutgers University, who will talk about some trigonometric identities associated with the roots of unity. As usual, please mute yourself, but you are welcome to unmute yourself anytime to ask questions or comments. Thank you.
Okay, thank you very much for the invitation and the kind introduction, Doron. So, okay, Doron already mentioned what's the title of my talk. And in the age of the pandemic, I thought I'd give an introduction picking up on social distancing, right? So, of course, there's a mathematician social distancing here. So, after all, there has to be also motivation how one can possibly run into such kind of identities that I'm going to present later on. So 1/3 of my talk will be this introduction, 2/3 will be then about those identities and the related questions. So, okay, so what is going on? So you take a sphere, d-dimensional sphere. Mostly in my talk later on, d will be 1, the unit circle, of course, but of course, d equals 2 would be some model of the surface of the Earth if you want. But in any case, pick n distinct points on such a sphere, and I write them as vectors in the embedding space, Cartesian. So they have length 1. They are labeled. That doesn't matter. It's just for convenience for writing some things. And so I use this symbol here to indicate the number of points in that configuration. So we do not allow points to coincide. So now you take any pair of points in such a configuration. Then you take the Euclidean distance in the ambient space. So you do not go the geodesic distance, you don't take that one. So we call it d of these 2 points. And then you define the arithmetic mean distance to be simply, well, the arithmetic mean over all possible pairs in that configuration. Similarly, you can define the geometric mean. And here is, of course, I just noticed 2 typos. The R is missing. And by taking the product over all possible pairs and then the corresponding n choose 2th root of those. And what is the optimal? That's all copy-paste errors here. Optimal distances, you maximize those expressions. Okie doke. And so these are the letters. Okay, here are just as a potpourri of some optimal configurations on the circle. Well, of course, everybody knows when you have just 2 points, then optimum is when they are antipodal. When you have 3 or more points, they are all known. That's a regular n-gon, namely the roots of unity up to rotation, of course. D equals 2 is more interesting. Of course, 2 points, the same story. 3 points is also the regular trigon, that's equatorial equilateral triangle. But now with 4 points, you already become 3-dimensional. You have a regular tetrahedron. 5 points is a regular triangular bipyramid. And notice also when I take 6 points, that's the regular octahedron. So far, the optimizers are the same. Doesn't matter whether you take arithmetic mean distance or geometric mean distance. But when you take 7 points, it's already more interesting. Then you get different answers. And then for just filling the space below, I took also 8 again. That's a unique answer, twisted cube. 12, that's the regular icosahedron, as expected. But the more you go on with larger n, it gets more and more tricky. And even what I wrote here, not all of that is truly rigorously proved, no? But icosahedron, octahedron, tetrahedron, anything up to here, yes, is proved. Also the regular triangular bipyramid, and so let's go on. Now, if you have
Michael, in principle, it's a multivariable calculus problem, right? You optimize something with
except that it gets, that's right, except that it gets quickly out of bound. No? So remember a couple of years ago, I gave a talk about a joint project with an undergraduate, Renai. We took 3 points on the circle, but we did not just optimize, we asked for all equilibrium configuration. There were some surprises in there. So I thought everything had been sorted out before. It wasn't. So that's why we actually were able to publish a paper. And so even for 3 points, it gets quickly very complicated, but very fascinating also. Anyway, back to 7 points. So we got different answers depending on which mean we took, arithmetic or geometric mean. So which one is better? Well, the answer is it depends. Namely, Now here we have that dilemma. So if you take the arithmetic mean as a measure of things, then of course the optimizer here beats the optimizer of the geometric mean. But if your measure of things is the geometric mean, then it's the other way around. So you need some other principle that selects what type of mean you should use. And if, and that's of course just contrived now, if really only the highest numerical mean value that you can possibly obtain matters by really averaging over something, but you have only these two options, arithmetic or geometric mean, then of course by the inequality between arithmetic and geometric means, the arithmetic one beats the geometric one. So on the other hand, and when you go back to the literature on orthogonal polynomials, and it seems to have started with a paper by Stiltjes in 1885. And so he found that the root system of some orthogonal polynomials actually optimize the geometric mean distance. So he did it on an interval, and then Schur and Fekete later on generalized it to more general domains, including, for instance, you could think of the sphere. And but the interesting thing is then, of course, that whatever I have talked so far in terms of social distancing with geometric mean distance, arithmetic mean distance, you can associate this with some minimization of some arithmetic mean pair energy, and that you can generalize to a whole continuous parameter family. So let's look at that briefly. Maximizing arithmetic mean distance, of course, is the same thing as minimizing 1 minus it, right? That's not a big surprise, and that's already in the form of arithmetic mean. But maximizing geometric mean is equivalent to minimizing 1 over it, and then you take the logarithm, the log of a product, right, is the sum of logarithms, and so now you have an arithmetic mean of the logarithm of 1 over the Euclidean pair distances. And indeed, these are just two special cases of a whole parameter family, and they are indexed by parameter S, the so-called Ries parameter, named after Marcel Ries. And so you average now, when you choose S, the Ries pair energy that are defined on the next page over all possible pairs. So here's then what that is. And R stands now for a positive distance, Euclidean distance between 2 points. S is my real parameter, and I've defined it in this way. When S is not 0, it's essentially just 1 over R to the power S, but offset by -1, and then the whole thing multiplied by 1 over S. And when S is 0, then you take just the limit and you get the log of 1 over R coming out. In the literature, usually that is written separately. You take 1 over R to the S when S is positive. You take negative R to the absolute value S when S is negative, and you take ln 1 over R, but then you have to chop everything. So this is much nicer because it's a continuous family. Not only that, it's an ordered family of monotone functions. Namely, for fixed S, it's monotonic decreasing in the radial distance. For fixed radial distance, it's monotonic increasing in the Ries parameter. And there is an equality here, even only if R is 1. So of course, everybody knows how to plot powers and the logarithm. So, but anyway, so a whole family I included here. So this is S is increasing in this direction. And here's, of course, the radial distance. So there each function is radially decreasing, and 2 is the maximal distance on any of the spheres, of course. Okay, now you define the optimal average S Ries pair energy of such a configuration to be the infimum over it. In fact, an infimum exists when S is bigger or equal than 2, but not necessarily when S is less than -2. I have a brief remark on that later on. But what you can show about it is that for each n bigger or equal than 2, of course, the map into the optimal Ries pair energy, average Ries pair energy from S into it, that's monotonic increasing. That's a calculus problem just. This is also not difficult to prove that for fixed S, this map from the number of points into the optimal average Ries pair energy is also monotonic increasing. Moreover, when S is less than the dimension of the space, then that map is bounded above. And so, you know, an increasing and bounded function has to converge. So people are interested in computing then what the answer is when n goes to infinity. Moreover, when the Ries parameter is -2, then you can compute this answer in all dimensions. So this has to do with some Euclidean geometry part that is a very degenerate case. And so this is the answer you obtain. And that's 2, no matter which dimensional sphere you pick, for all n bigger or equal than 2. And as I said earlier, the minimizer actually exists when s is bigger or equal than -2. But of course, how do these things look? So now I looked at only up to 7 particles, but now pretty much the whole S range. Well, at least I start at -2, we'll put it this way. Again, in D equals 1, it's always 2 antipodal points. That's trivial, but when n is 2, or when n is bigger or equal than 3, it's always the regular n-gon. And even that is not so trivial to prove. It was known for s equals -1, that corresponds to the arithmetic mean distance maximization. And when s is 0, that was the geometric mean maximization. But to conclude that this is true for all s bigger than -2, that was a deep result by Kohn and Kumar that I will get to a little bit later again. But then in D equals 2, okay, 2 antipodal points when n is 2, equatorial triangle, we got tetrahedron, that's as before, but now notice even the 5-point problem now already splits into 2 configurations depending on what S is. And before the pandemic hit, we had a colloquium by Rich Schwartz from Brown University. He gave a computer-assisted proof of that phase transition here, and he coined the word she for this number, so this has a name. And then you go on, 6, regular octahedron, and now look, 7. It's already much more complicated. Before we had that split into these 2 configurations, but now when you make S bigger and bigger, there are several structural phase transitions between the optimizers. So it gets really, really, really fascinating what's going on here. And of course, when you make the number n bigger and bigger, you need a computer. It's very difficult to prove anything here. And here are some pictures. That is from a joint publication with Rachele Nerattini from Florence and Johann Brauchart from Graz. And so we pooled together data available at various web pages and from PhD theses up to 200 points on the 2 sphere. And so the selection of S is here. We didn't plot S equals -2, of course, because that's explicitly known that you don't need experimental data. The X here stands for experimental data, right? So these are not rigorously known optimizers. These are all numerically found by people running some kind of algorithms. And what we did is we plotted this. And well, for each fixed S, the function is increasing as n in n as it should. However, when you push this to further than 200, right? So we checked something and we found 24 outliers where this experimental curves were not increasing. So these were clearly wrong data then. It doesn't tell us what are the optimal data, but you at least know these are not right. And but also as S increases for fixed n, you see that here is a monotonic ordering. And so this is as it should be. But you also notice something interesting, that overall these curves seem to be concave when you think of the discrete second n derivative. So that raises now an interesting question. Are these curves concave, right? So here's the question. Is this map from the natural numbers with bigger or equal than 3 now, of course, because you take a second discrete derivative, is it concave for each such n and all s bigger or equal than -2? And there is an asymptotic large n analysis by Brauchart, Hardin, and Saff, and that reveals that the leading order term, when n gets really large, is indeed concave, right? And therefore the function will be overall concave when s is not bigger than 2 times the dimension of the sphere. However, it's overall convex when s is bigger than 2 times the dimension. And so that means that our map we are interested in from n into the average optimal free spare energy can only be concave when s is not bigger than 2d. Question now becomes, is it concave when s is between -2 and 2d? Well, for s equals -2, that's very easy. Pretend n would be just a real variable. You take the second classical derivative, you get this expression clearly strictly negative? Yep, that is strictly concave. Then, well, we don't have any more expressions in d equals 2, right? And so what we did, we inspected the empirical data again and took the discrete second derivative. Here it is, and here's what we found. Namely, when s is -1, we found strict concavity empirically, so experimental in this sense. But when s is 0, 1, 2, or 3, that's the data sets we had, there are convexity defects. And that set of convexity defects grows with the s, right? So you never lose a defect in the set, you only keep adding to it. And we use this criterion to check some databases, and we found 3 more outliers where you didn't have concavity, even though that is an empirical result. But once we had outliers, then we were doing our own optimization routines, and we found better configurations, and then the defects reappeared. So this seems to be a quite successful or promising test case for these empirical data points that one gets. So we were able to prove the occurrence of convexity defects, but we could not prove the strict concavity of this map when s is -1. On the other hand, having proved that this is strictly concave when s is -2, there must be a neighborhood by continuity where there is a still strict concavity is 2. The question is, how large is that neighborhood? Very difficult for us to find any answer for that in 2 dimensions. So let's look at d equals 1. And now part 2 of my talk, that was all introduction, right? So now comes the roots of unity. I mentioned before the work of Kohn and Kuma in 2014. And all endpoint optimizers are known for s bigger than -2 and can be identified with the nth roots of unity on the unit circle, right? So it's up to rotation on the unit circle and maybe permutation of your indices. And it's easy to work out what is the average Ries pair energy of the roots of unity. I indicated by an index 1 here. And this is what you get. This is simply summing over all possible angles, but you pick just one fixed point out of the n, and then you ask what are the distances to all the remaining points, so n-1 of them, you average over those. And of course, this 2 times sine of k pi over n is exactly are these distances in such a configuration. And that's the Ries power, of course, that you have here. No? So that's what it is. So we want to investigate this. So, and I mentioned here that when s is -2, then these are also optimizers, but there are many others, so they are not unique anymore. And when s is less than -2 and n is even, then the configuration collapses to 2 antipodal points, but each antipodal point now contains half of the original number of points that you have put in the configuration. If you think of particles, then they segregate into 2 parts, and one lives at the North Pole and one at the South Pole if you want. But if you have 3 points, for instance, then you can push below -2, and then the equilateral equatorial triangle, that means the third roots of unity, are still optimizers when s is bigger than this number, and that number is less than -2. Okay, so, but if you have such a nice formula like this, you look up integral tables or series and products, Gratstein and Rischig, and here's what you find. I just mentioned 2. S is -2 corresponds to that result. S is -1 corresponds to this result. Here are the numbers where you find the formula in this big book, the collection of data. And if you then ask for what is the second discrete derivatives, well, you get back, of course, here at the moment, of course, is not yet the second derivative. It's just the average Ries per energy itself. That's the old formula we had already, but we know it's also concave. And when you take s equals -1, then this is your average Ries per energy. And you can imagine that using a little bit of calculus, you can prove that this is also strictly concave. Then you go on and you find a product, and that is related to s equals 0. That means the geometric mean distance formula. And this is what you get for the average free-spare energy when S is 0. Also a neat little formula. And also that can easily be proven to be concave. So we are so far doing fine. But we didn't find any formulas in Gradzin-Rijik for other values of S, in particular not positive. So then you start using Maple, and now it's no longer experimental in the sense the data are really from that formula. It's now just plotting a formula, and you plot the second discrete derivative. And here is how that looks. So here's a selection of S values, now always positive, 1, 2, 3, 4, 5, and 6. And this here just means I plotted the 0 line. And so for S equals 1, it looks concave. For S equals 2, right? So you have the optimal re-spare energy. So this is not yet the second derivative. That's still the average re-spare energy here. Looks pretty much like a straight line. And then all the other curves look convex. So now comes the second discrete derivative. And indeed, for the original linear curve, now they come smack out on 0. The concave looking curve indeed produces a second discrete derivative that's negative, and the others are positive. So, and remember, we are in D equals 1 dimension, S equals 2 is 2D. That is exactly the borderline case coming from the asymptotic analysis of Brauchart, Harding, and Saf. But it's, of course, only discrete values of S that we used here, because that's, of course, also easier to compute even with Maple when you don't put 3.14 whatever in there. So here's then a conjecture you come up with, namely that continuously when S is between -2 and 2, right, then you have strictly concave behavior, an affine linear behavior, that means also concave but not strictly concave, when S equals 2, and strictly convex for S bigger than 2. That's the conjecture. And for special values S equals -2, -1, 0, that we just saw, that is actually true there. And for S equals 2, I will prove that below, coming up. That's based on the results by Johann Brauchart. And a proof of the complete conjecture for continuously varying S is supported by some Maple plots. I show them here. Here's now S, not R. And so you select now N, being from this set from 3 to 10, I did that. And you see that the second discrete derivative for fixed N varies with S in a funny way. They all hit 0 when S is 2. They are negative when S is less than 2, and positive when S is bigger than 2. That supports the conjecture, but of course, this is still only empirical evidence. So, but possibly with some rolling up the sleeves and doing some advanced calculus, one should be able to prove this. But now we go to the second conjecture, and gets more and more interesting for you guys. Namely, as I told you, that the map for V sub 2, that means S is 2, looked linear in N. So, okie doke, so you use Maple and actually look at the difference, what's the slope, and it always comes out for many values of N to be 1/24. And then you subtract N over 24 from this computation of V sub 2N, and you get always -11/24. So, wow, here is your computer-generated linear function for V sub 2 of N. Right? But, of course, I had plotted also the second discrete derivative for various different S values, and it turned out that in the second discrete derivative of V sub 4, that thing looked pretty linear. So you take now the fourth discrete derivative of V sub 4, and it comes out smack on 0. Is there possibly a polynomial dependence going on, right? So here is that empirical evidence. Conjecture 2. Whenever S is a positive even integer, right, then the average S re-spare energy of the roots of unity, that means this map when D equals 1, is a polynomial in N of degree 2m-1. So that was a conjecture. So I wrote at the time, we were having our collaboration on the paper by Nerattini, Brauchart, and myself in JSP. So I communicated that to my colleagues. And then I was amazed when Johann Brauchart wrote back that he had recently proved a related theorem inspired by results proved earlier in joint work of him self with Hardin and Ceph. In fact, he proved two theorems, one for negative even s and one for positive even s values. And here is the first one. Theorem. That's for negative s values. Now that means m is a natural number. And then the sum k equals 1 to n minus 1 over sine to the 2m of k pi over n equals this expression times n. So that looks pretty much linear, but notice there's another n here. Okay, so this sum over k includes only those k that are divided by n, and it vanishes when n gets bigger than m. That means eventually you only have this term, this times that, multiplied by n. So eventually it's linear, but this whole thing is piecewise linear. Except, in fact, when m is 1, then you have s squared, and then it is truly linear. But when m gets bigger, it's piecewise linear. And here's then the amazing theorem that when s now is positive, 2m with m in n, then that is what Johann proved, that you take the negative 2mth power of sine of the angle k pi over n, and you sum over k from 1 to n minus 1. And this is what you get. So this is truly a polynomial in n, even powers of n enter. This is the Riemann zeta function, of course, evaluated at this argument. And the alpha sub k of 2m, they are defined in a paper by Johann Brauchart earlier to be coming from this generating function. So you take the reciprocal of the sinc function, SINC, of pi z, take the 2mth power, and then Taylor expand it in powers of z, and that defines the coefficients a sub k of 2m here, right? So that converges when absolute value z is less than 1. And so interestingly, the previous theorem, right, has a relatively short proof. It's half a page that Johann has is by explicit computation. This here is a long proof, right, not so short, and it's massive computation. So it scares me when I see what he has been doing, but it's all coming out algebraically as identities at the end of the day, right? And I will explain later how one could possibly get the idea that this could be a polynomial, right? So here from Maple, of course, you got that idea already empirically, but Johann wasn't doing these Maple type experiments. So, and in any case, here's then the corollary that follows, and that is not about the average Ries pair energies, but it is the Ries as energy of an n-point configuration, that means the nth root of unity, divided by the number of roots, not by the number of pairs. That function is given by this expression and by definition, right? And this is what it comes out to be with Johann's formula. And that thing is strictly convex at each n bigger or equal than 3. And the point is that in the paper by Brauchart, Hardin, and Ceph, they observed that the sign of this is determined by the zeta function. So, right? And so that zeta function is only negative when k is m. These guys are always positive. So that means you have one negative term when k is m. But when k is m, this is a constant. So that doesn't affect the convexity. Here's another term with a negative sign, but that's a linear term. That doesn't affect the convexity either. And all the other terms have positive coefficients with positive even powers of n. So this is convex. Okay. But of course, it's not telling you whether the average Ries pair energy, pair average, no? So that this one is convex. So, okay, so let's plot, compute explicitly some special cases. And so when m is 1, you get this neat formula. When s is 4 means m is 2, then you get that neat formula. And then one more, you get this neat formula. And one thing transpires is that you always get the factor n minus 1 times n plus 1. Okay, at least the first 3 times. No? So of course the computation gets more and more lengthy to do this. But so a priori, this beast, of course, no, is defined only when n is bigger or equal than 2. But it turns out to be a polynomial that can be extended, of course, to smaller n values. And that seems to always have a 0 when n is negative 1, which is neat because remember when I go back here I have an n-1 with a minus sign, and if this here is always proportional to n-1, then I can factor it out, and that means I would get the same convexity type conclusion, except for the strict part, that will not be true when little m is 1. No? That means s is 2 in that case. Then you get linearity, but which you see is actually true here. No? It's linear in n. And but here you get linear times quadratic, it's convex. Here you get linear times quartic, which is convex. So that looks good. And so as an observation, this generalizes to all even positive s values as well, at least to as many as I was checking. So here's now, based on that, a conjecture, namely that I abbreviate now this expression here by sigma of m. That means in that polynomial that Brauchart wrote down, you just plug in n, capital N equals 1. So then all these n to the 2 times n minus k upstairs, this is all 1. So you get this sum, and that should always be 0. That's an identity that should be true. Now, let me first give you what I'm trained originally, as you know, as a physicist, so I always enjoy going sometimes back to mathematical voodoo arguments, why this should be true, right? And then
sorry, Michael, it's a beautiful conjecture. So this is still open, this conjecture?
At the moment, I would say it's still open, but I will convince you that I think it can be nailed down. Huh? So, in fact, I dabbled.
Remind me again, what's the alpha sub k of 2m? It's in the previous slide.
Yeah, it's on the previous slide, not the previous, but one of the previous slides. Whoop, wait a sec. No, I'm already too far back. Whoop. Yeah, here it was. I went too far back. This is the generating function. Okay, no? You will see it in a moment again.
Yeah, okay, sorry, thank you. Beautiful.
So this is the conjecture, no? Based on the first 3 terms that I have computed explicitly with this formula, meaning when m is 1, 2, and 3. I did that, no? So, I mean, by now I went much further, but anyway. And so I give you then later on the mathematician's argument that I say this provides convincing evidence, and I think I can finish this. And so in preparation for this talk, I was dabbling in trying to actually finish the proof. So here's first the physicist proof, right? So, okay, Brauchart proved that this is true for all n bigger or equal than 2. And on the other hand, the left side is a polynomial. So that is also well defined when n is 1. So, well, then that must be okay also on the right side, right? Why not? So if you set n equals 1, though, then you get this expression, k equals 1 to 0. Of course, this is bad, right? If k is 1 here, then it's 0, and 1 over 0 to some high power, or k equals 0 is not better. But on the other hand, don't mathematicians always say that summing from k backwards, whatever you sum is 0 by definition? And doesn't it make sense physically anyhow, because one particle doesn't interact with any other, so its interaction energy is 0. So this must be true, QED. So that's the physics proof. No? Of course, I enjoy this always very much, because it's, of course, not an argument that you should buy. So here's now mathematical evidence. So you see this generating function again. I'm simply splitting this into a product of its generating function, evaluated with 2k derivatives, and then you set z equals 0. No? That gives you this coefficient. And of course, the zeta function at the even positive integers, including 0, interestingly, is given by this formula, where these are the Bernoulli numbers. This one is a 2 times m minus kth Bernoulli number, defined by its own generating function. Right? Okay. And so this includes the case k equals m when zeta of 0 is negative 1/2. So this comes out right here. And all right, so we are here, and now stick this into your summation for that bold-face sigma of m, and that's what you get. So this is, I go very slowly through this, don't get scared. So here's your sigma m. I plug this definition in, but I already made some cancellations, so that is not too difficult to see. Here is still a pi z, and you don't see a pi z anymore, because when you take a good look, there's also a pi here, right? And so you can imagine that by doing a change of variable that you can get rid of some factors pi, and indeed they are gone. And so that's the first step. Then step number 2, I get rid of this -1 to the k by noticing that, well, here's the sign from the sinc function, but of course, if I switch to iz here, not there, only there, then I can absorb this as a power of I, and you see the sinh function now showing up down here. Okay, so I got rid of that baby. Moreover, you see suddenly there was a z here, now there's a z half. Why? Well, there was a 2 to the 2k that's no longer here. So I brought that in by a change, another change of variable. Okay, next. Turns out that when you take a good look, of course, this here is always an even function in z. So any odd derivative would give you 0 when you evaluate it at 0. And so instead of summing k equals 0 to m, what you see is actually all the even numbers. So I extend that now, rename k if you want. Now I go up to 2m, and instead of 2m over choose 2k, I have 2m choose k here. And these are now just the kth derivative, not 2k. And of course, here's 2m minus k instead of 2 times m minus k. Now you recognize the Leibniz formula for the 2mth derivative. Here we go. So this whole baby becomes this. And it's just the product of that guy times this guy. Now, there are various ways you can rewrite this, but I chose for these slides one particular one, namely, remember, this is a linear combination of e to the z half and e to the negative z half. And so how about you pull out the e to the negative z half downstairs? That brings it upstairs. But then there's also power 2m. So the z half with power 2m becomes just m times z then here, right? And the rest becomes this to the corresponding power. So, and when you look at this expression, this you recognize possibly as being a generalized Bernoulli polynomial. Namely, this is now, this whole thing here is the 2mth generalized Bernoulli polynomial of order 2m plus 1 evaluated when the argument is m itself. And that that exists in Wolfram alpha. So you plug that in and you check it, and I checked it then for many, many m's, and it's always 0 coming out. So this is my empirical experimental mathematical evidence that this is really true. And I spoke also with Siddhartha Zahi on some questions. So this is a polynomial now, right? So there are some tricks you can play with summing polynomials. And I'm pretty confident that one can prove this to be generally true, but I'm not completely done yet. Possibly you can also do.
So Michael, so you have a proof modulo this last.
Yeah, I mean, you could say that modulo showing that maybe by induction, yeah, so that it's definitely true for up to m equals 20, right? So that's already pretty large. And then if
but this is a Bernoulli polynomials.
This is always, yeah, this is generalized Bernoulli polynomials of order 2m plus 1, evaluated at m. Now, normally, instead of
probably well known, I think it's equal to 0.
They are pretty well known. I also found a book by Dilcher from 1984 called Zeros of blah blah, including generalized Bernoulli polynomial. Yeah. But he has even more generalized Bernoulli polynomials. So I would have to first dabble more in number theory.
I'm almost sure you already have the proof that it's not.
That's not much to be proved here. If you prove this, then you are done.
Yeah,
okay. Then you are done.
I'm almost sure that it's known because it's beautiful.
Possibly, but I didn't find, there are so many zeros of Bernoulli polynomials listed.
Yeah, okay.
But I couldn't find this explicitly listed.
Okay.
That's very funny. Maybe I typed in the wrong keywords yet, no? But I looked a lot because I'm pretty sure this must be known. So. Anyway, so therefore here's my experimental theorem based on what I just told you. No, so you can always factor out n-1, and therefore this Ries pair energy when S is 2m will be convex at each n bigger or equal than 3. So. And here's then just a few examples relatively quickly. So we are nearing the end of the talk. So this is just confirming what I had said earlier. No? But here is now the interesting thing. How did Johann actually get to do that? So he worked with Brauchart and Hardin himself on an asymptotic large n expansion, and that's their result. So here is for each integer little n that you pick, you get an expansion for this expression. S is now any complex number except 0, 1, 3, 5, and so on. Okay, and so then this is some constant that is given here times n plus n to whatever s is. And then here you have this expression you saw before. And then comes a correction term, and that means it's an error term that is smaller than this power, but with coefficients that depend on the real part of s and on what n is. And the interesting thing is they observed that, of course, when s is an even integer, this will terminate. No matter how large you make n, this will terminate at some point. And so therefore, the conjecture was this must be a polynomial. Right, and then what Johann's theorems, two theorems say, it is true, it is a polynomial when s is a positive even integer, but when s is when s is -2, but when s is -2m with m bigger than 1, then it's piecewise linear and therefore not a polynomial. So when I wrote that cautionary tale for experimental mathematicians, because you would have infinitely many cases where it's always true, right? But here there are a few slips, right, where conjecture of a polynomial would be false. And now that's of course small n, but what about that happens at only at n equals a gigazillion, and you won't find that experimentally, So anyway, so here are then some things to try for experimentalists. So Brauchart's proof is a tour de force, but the formulas look simple at the end. Is there a computer algebraic proof of his theorem that is giving also maybe closed form expressions? Are there novel integer sequences? Maybe. What about when s is an odd positive integer, right? So then it doesn't terminate, but can we at least find closed formulas? Oh no. And so then here, many thanks to Johann, to Siddhartha, Doron, and all of you. And here's the bibliography. I'm way ahead of time. We have time for questions.
Thank you very much for a very experimental and insightful talk. And we have time for questions. Any questions? I have
Can we
plenty
hear
of
your
questions.
conjecture about the Bernoulli polynomials again?
Yeah, I bring it back up. This is actually for a particular zero of the Bernoulli.
Yeah, of course, of course.
Yeah, oops. Here, that's the conjecture. Yeah, and so that here at the moment you don't see the generalized Bernoulli polynomial. That is after my transformations that I showed you, starting here, blah blah blah. You go all through, and then down here that it is that the 2mth generalized Bernoulli polynomial of order 2m plus 1 evaluated at argument m vanishes. So that means m is always a zero of that type of polynomial. So then the generalized polynomial itself, to get that one, you get that from this formula here, from the 2mth derivative of this expression, except that here would be an x. Instead of the mz, you would have an xz, and that m turns into an x.
Right. Okay.
While this m here, this m remains the m.
So this is rewriting it. So basically the conjecture is the derivative of order 2m. You take z over
you evaluate
z minus 1 to the power. Oh, that's beautiful. Okay, so we don't have to mention the word Bernoulli. So basically,
that's actually true. Yeah, that's true. You
so z over ez over e to the power z minus 1 quantity to the power 2m plus 1 times e to the power mz. Now take the derivative 2m times.
Right. And then
plug in z equals 0.
Right, exactly.
Then you get 0. That's the conjecture.
That's the conjecture, yes. And
beautiful.
Moreover, you can actually bring that also. You see that when you, the reason I wrote it is because this brings you the generating formula for the generalized Bernoulli polynomials. But you can do something else that I like even more. See, what I did here is I rewrote that part to look like this to some power. But of course, you can go the other way around and rewrite this beast to look like that,
Yeah.
right? Of course. And then you get, instead of e to mz, you get e to negative z half. And here,
Yeah.
instead of this beast to the power 2m plus 1, you get that beast z half over sinh z half to the power 2m plus 1, right? So the m only shows up now as a power here. And then here you have e to negative z half. Moreover, yeah, this is then an even function. And if you take the Taylor expansion of e to minus z half, of course, you get even and odd terms, but as a sum, you pull that out, and then all the odd powers then at z equals 0 will vanish. So that means that's this, you can replace the e to negative z half by the arithmetic mean of e to negative z half and e to positive z half, and you get the hyperbolic cosine then coming in.
Yeah.
And then you have just a relatively simple expression of an even function, a weight function that is the cosh of z half times the 2m plus 1 is power of z half over sinh z half, right? And then you can even pull in the 2 to the m here, make a change of variable and get rid of the halves, and it's really in z. So you can make that neatly compact, and then the conjecture would be the 2m derivative of that beast is also 0 when you evaluate it at 0 equals 0.
That's very nice. But going back to the penultimate line, if you
Absolutely.
replace the line before it, so you have a 2m's derivative. So if you take one less derivative and plug in z equals 0, you also get numbers. So maybe you have a source of sequences. So in this case, it's a 0 sequence. So maybe you have interesting sequences if you take less derivatives.
There may be lots of interesting things. That was one of my questions at the end, whether there is anything that is not already on Niels' OEs.
Yeah.
Because, of course, Neil has a ton of results on generalized Bernoulli polynomials and Bernoulli numbers now.
Yeah, beautiful. Are there more questions or comments? Thanks for a very experimental and fascinating talk. Thank you. So
very welcome.
Yeah, thank you. This ends this seminar. Thank you very much, and see you next week. Thank you. Bye-bye.
Thank you all for attending.
Thank you.
Bye.
Bye.